Hi guys, welcome to today's video, which is just going to be an introduction to the concept of the mole. Now, in chemistry, the mole is a unit of measurement, and we use it to try and allow us to get an understanding of how much of each chemical we need in a reaction. So if you're actually looking at an equation, so just a simple one like this, where you've got hydrochloric acid, and you're reacting that with, say, sodium carbonate solution, okay, and then we get obviously sodium chloride, carbon dioxide and water as a product. That's not important. What the mole allows us to do is to identify how much of each reactant we need, or of a species we need, to be able to react. So in an equation like this, the numbers out the front are what are called the stoichiometric ratios, okay, or sometimes they're referred to as the mole ratios of a reaction. So this is telling us that we need 2 moles of hydrochloric acid for every 1 mole of sodium carbonate. So the number out the front tells us the number of moles that we need. However, you don't go to a shop and you don't order 10 moles of something. So you always order it by a per weight or a per volume, so either grams or milliliters or liters. And so what we use is the mole along with a couple of equations to work out how much of substances we need. I've covered those in some of the other videos on calculating mass of a substance and calculating number of moles of a substance. So I'm not going to go into that today. So what I'm going to do is just simply explain to you around the mole, what's called Avogadro's constant, okay, and how that relates to chemistry. So Avogadro's constant was worked out by a chemist, and he worked out a way that we can compare lots of different species and how many atoms or particles there are in there. So this number of 6.02 by 10 to the 23, that relates to the number of atoms or molecules or particles that there are in a certain species when there is 1 mole present. Now, what is 1 mole? Okay, well, 1 mole relates to what we call the molar mass of an element or a molecule or a compound. So if we're talking about an element, if we look at something like sodium, for example, sodium has an atomic number of 11 and a mass number of 23. So if we're just talking about a sodium atom, the mass number up here, 23 grams, that tells us that we need 23 grams of sodium for 1 mole. And so those 23 grams of sodium will have 6.02 by 10 to the 23 sodium atoms. Okay, so 1 mole of a sodium, all right, is 23 grams. We get that from the periodic table, the mass number, and that's equal to 6.02 by 10 to the 23. That's Avogadro's constant. So if we take water, for example, H2O, you want to be able to calculate the molar mass of water. Now, I'm not going to go through how you do that in this video because there's another video on that as well. But very quickly, you just add up your 2 hydrogens and your oxygen, and you end up with a molar mass of 18, okay? 18 grams. Now, what that means is that 18 grams of water is 1 mole, okay? And that is equal to 6.02 by 10 to the 23 water molecules. So you can see now how the mole is actually a really good way for us to be able to start identify or to compare different substances. Okay, if we were doing a reaction between sodium and water to produce hydrogen gas and sodium hydroxide, we would need to know how much of each to react. Now in that equation, all right, of sodium plus H2O, so Na plus H2O, to give us hydrogen gas plus sodium hydroxide, okay, we need to balance this up. Double check that I've done that right. Yep, there we go. So what this is telling us is that we need 2 moles of sodium with 2 moles of water to produce 1 mole of hydrogen and 2 moles of sodium hydroxide. Now, it's important for us to understand how much we are reacting, because if we just chuck a whole bunch of stuff in together without knowing how much we're adding, we're going to generate a lot of hydrogen gas. Now, hydrogen gas is quite explosive, so that could be quite unsafe. And so we use these sorts of calculations in our understanding of the mole concept to work out how much of substances we want to add in reactions. So here, if we were doing 2 moles of sodium and 2 moles of water, okay, we know that 1 mole of sodium is 23 grams. So we only need 23 grams of sodium and 18 grams of water for a 1-to-1 ratio. Now we wouldn't use that much, right? There'd be no reason to use 23 grams of sodium. That would be quite an exothermic reaction, quite dangerous. So we'd go much lower. But we now get a ratio of the masses that are required based upon the concept of the mole. Okay, so Avogadro's constant here, 6.02 by 10 to the 23, that tells us, as I said, how many particles or atoms there are in a species. So I'm just going to break that down a little bit more for you. So in order to break it down for you, I'm going to look at one of everyone's favourite molecules, glucose, C6H12O6. If you calculate the molar mass of glucose by adding up all the different atomic masses of each of the atoms in there, you get, and I'm just rounding it up here, you're going to get an answer of about 180 grams, all right? So that 180 grams is per mole, because 180 grams is the mass of 1 mole of glucose, okay? So if you weigh out 180 grams of sugar, that's the amount of sugar that's in about 3 and a bit iced coffees, okay? That amount of sugar is equal to 1 mole. Okay, so that 1 mole in that 180 grams, sorry, I've said 180, it might be 160, I'm not sure, that's not important at the moment. I'm sorry if I've got the calculation wrong, I'm doing it off the top of my head. So in that mass of glucose though, we have 6.02 times 10 to the 23 glucose molecules. Okay, now that's no different from what we just said before. But if we start breaking it down, Avogadro's constant can be applied to the carbons, hydrogens, and oxygens in here as well. So within that glucose molecule, we actually have 6 carbon atoms, we have 12 hydrogen atoms, and we have 6 oxygen atoms, all right? That's within every molecule. So you've got your molecule as a whole, the whole big thing, and then we're breaking it down to each of the individual atoms in there. Now, in terms of the number of atoms we have, because we've got 6 lots of carbon for every 1 of glucose, we've actually got 6 lots of 6.02 by 10 to the 23 atoms of carbon in there, okay? So we've got this many molecules, but when you break it down, the carbon atoms are much smaller, and for every 6 of them, we have 1 glucose molecule. So we've actually got 3.6 by 10 to the 24 carbon atoms, all right? That's just using scientific notation. There is a video on that if you want to have a look as well, okay? So 3.6 by 10 to the 24 carbon atoms. Likewise, if we work out the hydrogen, we just multiply 6 12s, 72. So we've got 7.2 times 10 to the 24 hydrogen atoms. And for oxygen, we've got the same as we had for carbon, so we've got 3.6 by 10 to the 24 oxygen atoms. So this is really important, all right, when you're going through and doing, as I said, chemistry reactions or calculations. You need to have an understanding of what a mole is. So a mole is a unit of measurement that we use to be able to identify how much of a substance we need, and that's related to this Avogadro's constant, where 1 mole is 6.02 by 10 to the 23 particles or atoms, and that goes for anything. So 1 mole of any substance is 6.02 by 10 to the 23 particles. Whether it's an atom like sodium we looked at, whether it's a molecule like water we looked at, whether it's a big molecule like glucose here. 1 mole of glucose is this many glucose molecules, but you can actually break it down and work out how many atoms are in there as well. So this is a brief introduction to the mole. As I said, there's a few other videos you might want to check out. One of them is around scientific notation and converting scientific notation if you're not sure around that. The other one is around calculating mass of a substance, number of moles of a substance, or molar mass. All of those will be useful for you as well. All right, hopefully this has made sense. You might want to watch it again. It's an interesting concept to get your head around for the first time. Thanks, guys.